When we train a classifier, we usually tell it the answer in the harshest possible way. This class is correct. Everything else is flat wrong. Put all your probability on that one option. The model happily obliges, and it starts pushing its confidence to extremes it hasn't really earned. Over time, it becomes the student who's sure of every answer, even the ones it got right by luck. Label smoothing, introduced by Szegedy and colleagues back in 2016, is a tiny change to how we phrase that answer, and it fixes a surprising amount of that overconfidence. Let's unpack exactly what it does and why it works. Here's the contrast at the heart of it. It all comes down to the shape of the target we ask the model to match. Normally, the target is a hard vector, probability 1 on the correct class, exactly 0 everywhere else. To match that, the model has to drive the right logit toward infinity, which makes it overconfident and poorly calibrated. It ends up saying 99% when it should really be saying 70%, and that gap between confidence and correctness is exactly the problem. Label smoothing softens that target instead. We keep most of the probability on the true class, say 90%, and sprinkle the small remainder across every other class. Now, the model has no reason to blow its logits up to infinity, so it stays calmer, generalizes a touch better, and its confidence finally starts tracking how often it's actually right. So how do we actually build one of these softened targets? The recipe is short, and it's the same every step. First, we start from the ordinary hard label, the vector that names exactly one correct class with everything else set to 0. That's our raw starting point before any smoothing touches it. Then we choose how much probability to keep on a true class. Something like 90% is common, leaving a small budget of 10% to redistribute. That kept mass still clearly marks the right answer. Next, we take that leftover budget and spread it evenly across all the other classes. Every wrong option gets a tiny, equal share, so the target becomes a gentle hill instead of a single sharp spike. Finally, we trained the model toward this softened distribution rather than the hard one. The loss stops rewarding infinite confidence, and the network settles into predictions that reflect real uncertainty. Now, why does such a small tweak earn its place in so many famous architectures? 3 ideas carry it. It softens the hard target. Instead of demanding certainty on one class and 0 on the rest, it asks for a realistic distribution the model can actually reach without going to extremes. Because the logits no longer race to infinity, the model becomes less overconfident and far better calibrated. Its stated probabilities start lining up with how often it's actually right, and it acts as a light regularizer. That small deliberate blur in the labels discourages overfitting and tends to nudge generalization up a notch, which is why Inception and the Transformer both use it. The only real cost is a sliver of intentionally wrong signal in the target, and in practice that's a bargain. Let's pull the thread together with 4 things worth remembering. Label smoothing replaces the hard one hot target with a soft one, keeping most probability on the true class and spreading a little to the rest. Because the model no longer chases infinite confidence, it grows less overconfident and produces better calibrated probabilities. The cost is a small amount of intentionally wrong signal in the target. The payoff is regularization and usually slightly better generalization. You'll find it inside Inception, the Transformer, and countless vision models quietly doing its job. Want more of these one-idea AI explainers in plain English? That's exactly what we make over at Standarity.com.